Hello and welcome. In this Max tutorial, we're looking at sampling techniques that treat input textures as control data. So this is the third video in a series on some fundamental jit.gl.pix Codebox techniques. So the idea is that instead of doing larger patches on very specific visual effects like I usually do, I want to showcase some more general concepts, and each video will be self-contained and hopefully a bit more beginner-friendly. So some of the concepts I'm discussing here can also be found in some previous tutorials I did, but then of course in the context of different topics. So before we start patching, maybe we should go over the concepts and what this video is really about. So the idea is that a texture is not just an image, but it's a structured data container. So a texture is essentially a 2D array of values. Sampling in this context means reading a value at a specific coordinate and then doing something with it. Those values usually represent color, but they don't have to represent color. They could represent something like indices or positions or whatever arbitrary control data you can think of. So in this tutorial, we will use textures as data-driven control systems to influence or control other textures. This video consists of 4 parts. In the first one, we will use textures as color lookup data. In the second one, we will use textures as 2D position data. In the third one, we will use a texture for coordinate remapping. And in the fourth one, which is a bit more advanced, I guess, we will combine the second part, so the position data, and the third part, so the offset control, to make something a bit more complex and advanced. Okay, I am starting with a JIT world as our rendering context because, again, we're working with textures. Here I have a JIT P window, so we can monitor what we're doing, and here I have an input video. Okay, starting with the first part, the color lookup. So the idea is that we create a texture that stores color information, and then this texture will work as a 1D lookup table. Okay, first I will create this random lookup table or this texture. So let's create a texture. Let's say dimensions are full HD and type float32. Then I will use another JIT P window so we can see what's happening in here. In order to get random lookup colors in here, I will use a JIT noise. 3 planes, float32, and I will just hard code this to 10 colors. You could then, of course, change this number and also change it in the code, but just for demonstration, I think we can just stay at 10 colors. Then I want to constantly bang this texture, so we get the output, and I want to use a load bang in order to get the output here. So now you can see we have random colors, and the idea is now that I want to have this input texture and then, depending on the brightness of the pixels of the input texture, assign these random colors. Okay, to do this, I will just copy this one. So it's a bit more explicit that it's also full HD. Then I will create a jit.gl.pix Codebox, which is the star of the show here. Okay, let's put this aside. Then let's assign our inputs. So the first one, pick in, is just for the main input. This is input 1, so this will be the video input. Then let's call the second one color in. This is input 2. And just for now, we can set the output to 1. Then we can patch this in here. Input goes in here, and then the color lookup goes in here. Okay. Seems to be working, no errors. Okay, what I want to do now is I want to downsample the input texture. What does this mean? So if we're taking a look at it now, you can see that this is consisting of a lot of colors. So float 32 means that we have a lot of colors available. I don't know by heart how many this is, but you can do the math yourself, I guess. So first I want to go from all of the colors we have here to just 10 brightness values, which will correspond to these input colors. So in order to do this, first I will create a parameter, call this one num colors and set it to 10. So it corresponds to the number of colors we have here. Then I will create a variable, call this one downsample. And first I will use the RGB to HSL, use this one as an input, and then extract the Z value. So hue, so the color, the saturation, and the luminance, so the brightness, and I only want the brightness. So let's take a quick peek at what this might look like. So now it's just in grayscale, but as you can see, even if it's just grayscale, we have a lot of different colors within that grayscale. So I want to downsample this. So in order to do this, we can use the floor operator. So now you can see that, again, we have a lot of colors and they're in the range from 0 to 1. So in order to downsample this, we can say floor and then multiply this by the number of colors we have available here. So floor means that we're only taking the integer part of the number, and now that we're multiplying it by 10, or by the number of colors, which is 10 in this case, we know that the output will either be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So if we take another look, nothing happens because, oh, I forgot this here. So now you can see it's either black or white because we can only display 0 and everything that's above 1 will just be white. So in order to see these 10 values that we have, we can just divide it by the number of colors again. And now you can see we have these areas that basically consist of the same color. So now the values that this downsample variable can have will be 0, 0.1, 0.2, 0.3, up to 0.9. So this is like our downsample texture. If we just say 5 here, we will only get 5 grayscale values. If we say 25, or no, we'll have 25 of them. But now we only want 10 because here we're also just using 10. Now I want to access these color bins, and I will get rid of this division here because I want to access them by their index, so to say. So we need a number between 0 and 10 now. In order to access the individual colors, we first have to create the coordinates. So in sampling, we're using normalized coordinates from 0 to 1. So we have to bring this in a form that works between 0 and 1. So first I will create the size of one of those color bins. We can just call this one bin size. This is 1 divided by the number of colors that we have. So imagine we have these 10 colors, so this will be 1/10. So if we're starting at 0, this will be 0, then 0.1, 0.2, and so on. So this is the bin size. And then the actual bin we want to take a look at will be this bin size, so 1/10 multiplied by what we just downsampled here. So If it's the first bin, it will be 1/10 by multiplied by 0, so this will be 0, then 1/10 multiplied by 1, which will be 1/10, which will be inside here, then by 2 will be 0.2, 0.3. So we can multiply this by our downsample texture. But this won't quite work yet because this always represents like the beginning of the bin, because 0 is right about here, 0.1 is right about here, 0.2 is right about here. And this can lead to artifacts depending on what we're using to sample. So I want to have the middle of the bin. So in order to get in the center, we can just add half of the bin size. So bin size times 0.5. So now we moved from the leftmost edge of the bin to the center of the bin. So now we have the sampling coordinate, and then we can just use the sample operator and say, I want to sample this texture at this bin coordinate, and this bin coordinate is computed by looking at these downsampled colors here. And this is not working. Why is it not working? Function call missing. Where did I go wrong? So 1 divided by a number of colors. Oh. It helps if you spell it the right way. No, it's still not working. So bin size, okay, this needs to be capital letter. Okay, so now it's working. Beautiful, looking very psychedelic. And if I change the color lookup here, this will also change. So in this case, we're sampling this texture at this downsampled coordinate. So this is essentially just a color lookup. Beautiful. Okay, that's it for part 1. I will put this somewhere here, coming to part 2. So now we're going to use a texture as 2D position data. So we will draw rectangles and then use pixels inside of a texture in order to set their positions. So I will just copy this here. Let's put this away. So here we have the input. Then again, first I will create the positions. So I will just duplicate this one. I will create another P window so we can have a look at the positions we're creating. I want to use a jit.bfg. Let's say, okay, we need 2 planes because we will have an X and a Y position. Float 32. Again, I will work with 10 positions, so 10 by 2 by 2. So this is the minimum dimension that is required here. And let's say basis noise simplex, and let's use scale of 10. Then we can use a jit time in order to drive this. So we need to constantly create an offset and bang this one here. And then I will, so now you can see, okay, what else do I need? I need to first create a matrix 2, float 32, 10 by 1, and then say a depth 0, because I only want it to be one-dimensional. And then now you can see these colors are very bright because they're not in a scale of 0 to 1. So in order to change this, I can use jit normalize, and then the colors will be in the range of 0 to 1. Okay, and so these colors have an X component and a Y component that ranges between 0 and 1, and we can use them as 2D positions within our plane. So in order to do this, I will again create another jit.gl.pix Codebox. Yeah, I don't know how much space I will need yet, but let's see. Okay, I can plug this in here. Then, yeah, let's call this pick in again is input 1. Then position in is input 2, and out 1 can just be 1 for now. Oh, look at that. Okay, I will use the same function for a rectangle that I used in the previous video, so I won't go into detail how to create this. I will just quickly code it. So rect, this needs UV, this needs a scale, this needs a position. Then we can say X equals the position if it's smaller than our UVs, then we only need the X component of that. And of course, what also needs to be true is that position plus our scale is bigger than our UVs, and I also need the X component of that. Then I can copy this whole thing, turn this into a Y for the Y component, and then I would just return if both of them are true. Okay, so did I make a mistake? Okay, adapt is not valid. Of course. Okay, so here we have a rectangle, or the function for a rectangle. So what I want to do now is in a for loop, I want to create multiple rectangles, and for the position parameter, I want to use the positions that we created in this texture here. So in order to do this, let's first create our UVs. These are normalized coordinates. Again, we can say that the bin size, which is, if I'm quickly putting this in here, you can see that, oh, something went wrong. Oh, adapt 0, not adapt 1. Okay, so now you can see that we also have 10 bins here, and we also need the bin size as normalized coordinates. So essentially the same thing we did with this one here, with the colors. So we can say that the bin size equals 1 divided by, okay, first we need a parameter that tells us how many rectangles we want to use. Let's call this numRect. Then we divide this. So the bin size again will be 1/10, but if we change the number of rectangles, this will also change to the correct bin size. Then I will call these rectangles just windows, and let's set this to 0 for now. Then we can put this up here. I will encapsulate this. Just call this one No, not this. I will call this position texture. So we have a bit more space up here. Okay. So now we can create the for loop. So we can say for I equals 0 and I is smaller than the number of rectangles we want to draw. I plus equals 1. And what I want to do now is I want to loop, again, copying this one. In this loop, I want to, okay, this is going pretty fast. I think it will be annoying. So let's just say speed 0.1. Oh, much better. Okay, so that's probably too slow. Okay, so the idea is that I want to loop over each of those bins, and then for each bin, I want to take the position and then draw a rectangle at this exact position. So in order to do this, first I need to know which bin we're using. So bin equals, what did we have here? So we need the size of the bin. Then I need the index. So these indices represent the color bins. So 0 is the first bin, 1 is the second bin, and so on. So times I. And then again, in order to sample from the center of the bin, we can just say plus bin size times 0.5. Okay, so this will give us the bin coordinate. Then we can create our positions. So the position in this case is sampling the position input at this bin coordinate we just created. So we're peeking into this texture at this position or at this coordinate in order to get the positions out that we created here. So this is the idea. Let's call the next one mask. So this will be the rectangle that we're drawing. So here we can use the UV coordinates we used here. Then for scale, I can just hard code something, 0.25. And here the position is the position we just created. So then we can say windows plus equals mask. So this means that, so for every frame, we're doing this for loop and creating new masks or new rectangles and stacking them on top of each other. So at the beginning of the frame, this is 0. Then we're going through the first loop, adding the first window, going through the second loop, adding the second window, and so on. And this is why you have to be careful with using for loops in here, because essentially how this works is that this for loop is computed for each pixel in the texture. So if you use something like 1,000, then for each pixel, this would have to be done 1,000 times. Okay, let's see if this worked. Yeah. Okay, this was from before. So now we can see that we're drawing the windows at these positions we created here, and they're floating around. What I would also like to do is that the windows show the texture that's underneath them, so to say. In order to do this, we can do something like, maybe let's call this an individual window and say this is the mask we're using, and we're multiplying this by our input picture. And then, of course, we have to get rid of the mask down here and just add the window. So this is almost what we want to do, but if you take a closer look. So here, when they're overlapping, the colors are just added together because we're stacking them on top of each other, which I don't want to do. So in order to prevent this, we can say windows equals, and then using the mix operator, and then saying, okay, it's either the windows we used before or it's the current window, and this will be decided by the mask. So this means essentially if the mask is white, which it will be for the current window, then we will just see the current window. And if it's black, then we will see what has been done before. So this way they will also be stacked on top of each other, but there will be no overlap. Hopefully, let's see. No, because I obviously made a mistake. Where did I go wrong? Oh, of course. So now it's working. Now you can see that they're drawn on top of each other, but there is no like color overlap. Okay, so this was the second part of the tutorial. I will also put this, I don't know, somewhere down here. I will copy this for the third part so I can reuse it. Where am I? Okay, here. So just getting rid of all of this. Plugging this in here again. So coming to the third part, now I want to do some coordinate remapping. So the idea is that we create a texture that stores some coordinate offsets, and then we can use that to scramble tiles within the original image. I will create a list of indices, and then the indices will be turned into UV coordinates, and those UV coordinates will then decide for the input image how we will cut it up into different tiles, scramble them, and where to put them in the output image, so to say. So in order to create a list, I will use multi-slider object. No, I will do this here in the inspector because I always forget. Okay, we don't want a floating point output. We want a range from 0 to, yeah, let's do 10 again. Oh no, let's do 12 because then I can have 4 by 3 tiles. So not 10, so 0 to 11. And number of slider is also 0 to, oh no, number of sliders is just 12. So now the output, okay, 4 by 3. And these indices will then decide how we'll cut this input image. Okay, then I need to turn this into a matrix. So in order to do this, let's first create the matrix, jit matrix. Let's call this one index. This has 3 planes, float 32, and it's 4 by 3. And then we can use the jit fill object, also give it the same name as our matrix here. And then just to check, we can use a jit cell block. And now we can see the indices here. If we neatly arrange this, it should go from 0 to 11. Yeah, okay, this is essentially what we wanted. Now I want to create some code that turns these indices into UV offsets. So in order to do this, let's create a jit.gen codebox. I also used this in a previous video, but I did it a bit differently there because it wasn't just about scrambling it, but it was about rearranging the tiles so that each tile was there only once. But with this system, you could essentially have the first tile 12 times. To create the offsets, first we need the X offset. So in order to do this, we need to take the input of the list. I will keep this here so we can see what's going on. Again, doing this neatly so it's easier. Okay. The X offset is, or the X coordinate will be the input we're using here. So the number from 0, so the index, the number from 0 to 11. So in 1.x, and then we're doing modulo the dimension of x. So this means that it will go always from 0 to the number of cells we have in the x direction. So it will always go from 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So let's see if this is working. No, of course I have to say output 1 equals x. So now you can see 0, 1, 2, 3, 0, 1, 2, 3, which is essentially what we want because we want to have the coordinates on the x for the x axis. Then for the y, we need to do something else. So we have to look at, okay, so how many times did we cross over in x, and then use the floor function on that. In order to do this, floor in 1.x, then divide this by the dimension of x. So again, the floor function gives us the integer component. Now we're taking the index and we're dividing it by how often we're like crossing over to the next line. So each line is the new y index, and with this we're just seeing, okay, how often does our index fit into this, meaning how often are we crossing over into the next bin. And then we're only using the floor function, because if we don't use the floor function, it will look something like this. But here in the first row, we only want 0, so we can get rid of the floating point. So if we just say floor, then okay, x, so y is 0 here, y is 1 here, y is 2 here. And in order to get this into the range of normalized coordinates, so between 0 and 1, we can just divide this by the dimension of x and this by the dimension of y. And then we can say that our new position is a vector consisting of x and y we just created. Then we can copy this and maybe take a look. Okay, perfect. So this looks like normalized coordinates, but we don't just need the normalized coordinates we create here, because here we're going to add this offset. So here we have to create the offset. So the offset is our new position minus the normalized coordinates, which is exactly 0 now, which kind of makes sense because if we want to have this, then we don't want the picture affected at all. If we have something like this, we want to have it affected in terms of, okay, what's the difference between what we created here and their actual coordinates? Okay, again, creating this neat little thing again. Everything else will happen inside of our code box here. So I will create a texture, and what's important here is to give it the attribute filter none, because if we don't have that, then we could interpolate between those colors that we're creating here, and then we won't get the nice tiles anymore. Okay, then as I said, the rest is happening in here. So again, picture in is input 1. Then our offset is input 2. And then output will be sampling the input by UV coordinates, and now we have to create them. So the UV coordinates in this case are the normalized coordinates plus the offset we created here. Is this working? Yes. And this is why we have to do it. I think it's a bit weird or a bit counterintuitive to do it like this, because here we're creating a new position and then we're subtracting it, subtracting normalized coordinates, but here what we're doing is adding them back in. Okay, this is not what's supposed to happen. Maybe I also have to be clear about the dimensions here. Ah, okay, I see what's happening here. I have to create, we have to create our own UV coordinates here. So cell divided by the dimension, and then it should be working. Yeah, okay, now it's working. So essentially, cell divided by the dimension is a bit different than UVs. We can take a quick look at that to see where the difference lies. So maybe let's create a JIT cell block here. Let's create a matrix 2, float 42. Let's do something like 5 by 5. Oh no, that's not what I wanted to do. Okay, jit.gl.pix Codebox. So if we say output 1 is the normalized coordinates, you can see that this goes 0, 0, 2, 5, 0.5, 1. So this goes from 0 to 1. But if I'm doing cell divided by the dimension, this doesn't go from 0 to 1 anymore. So there is a slight difference in here. Oh, what's that? But we need it to not go from 0 to 1. And now if I'm scrambling these, you can see that I could just for each tile, this is not what's supposed to happen. Ah, okay, I just saw I made another mistake here. So now you can see that each one is taking the first one. Now each one is taking, or each one is set to the last one. If we do it neatly like this, you can see that we have the original and then of course everything in between. Okay, so this concludes part 3. In part 4, we're going to combine essentially what we're doing here with what we did in part 2. So we will use part 2 as a basis, and then have the windows not just floating over the texture that's underneath, but referencing specific tiles and then moving the tiles around. Okay. In order to do this, I will make some space again. Put this down here. Then I will just duplicate this because this will be our template here. So we need this here. Then what else do we need? We also need this input that we created. So I will also duplicate this. But I have to change the name of the matrix here because it's now referring to the same one. So let's call this maybe index 2, index 2. Then I also want to have this as a one-dimensional matrix because here, I will stop that for now. Okay, so I want this as a one-dimensional matrix because then I can go over it in the for loop. So in order to do this, let's change this from 4 and 3 to 12 and 1. Then I also need to change some code in here because then... No, you know what? I'm going to do it differently. I'm not gonna use this as an input. I'm just gonna use the indices that we have here and then use them to loop or to get a specific portion of this one. Should be easier, hopefully. Okay. But it's still kind of combining this one with the previous one we did. Okay, I have the number of rects, which is now 12 because I want each of those tiles. Then, or you know what, I could just say num rects and then make this two-dimensional, so it's 4 and 3. What else do we need to change? So bin size is... So this is now... number of rectangles x by number of rectangles y, so it will again be 12. But of course we have to change this in here because now we have 10 in here, like 10 positions, but we want to have 12 positions. Let's see if this worked. So 1, 2, 3, 4, 5, 6, 7. Okay, this seemed to work. Okay, what else do we need? First, so the bin size, this can stay the same. I will change the scale though, so the scale will be 1 divided by the number of rectangles. So this will be exactly 1/4 on the x-axis and 1/3 on the y-axis. Then we can copy this scale and put it in here where we just hard-coded something in the last version. Then, so let's look at it. So now you can see that the scale is the same, but the positions are not right because we're just scanning over the whole thing. So in order to kind of like take the original position with us. So to say, I have to create an offset. So this offset is, so now we have I here. So we have to turn this into what we originally used. So we have to create X and Y for our offset. So X in this case is, wait, what is it? It's I. So it's our index modulo the number of rectangles we have on the x-axis. And to get in a range of 0 and 1, again, divided by the number of rects on the x-axis. So this is essentially the same thing we did here, but now we're not using this index list, but we're using just the index of the rectangle within our for loop. Okay, so we have x here. Then y is then, yeah, also essentially the same as we had before. So floor of I divided by the number of rectangles on the x-axis. And then, of course, to get in a range from 0 to 1, divided by the number of rects for the y-axis. So this is the offset. Then we can't just, so offset, sorry, is a vector consisting of x and y. And then we can't just say we're using the picture in as it is, but we have to sample it with this offset. So we're kind of taking the offset that we're creating with, so each tile gets a position, and then of course the offset for the underlying picture, it just shows that specific tile that's underneath. I hope that made sense. Yeah, so the offset, no, we already got this. So in order, let's not call this pick, so we can just say, so pick equals sampling the picture input. And then we're using our UV coordinates plus the offset. And then we're not multiplying this by pick in, but by pick. So this is almost working now, but what we also have to take into account is that they are moving around. So the texture that's underneath them also has to move around. So I think we can just subtract the position, because imagine we're at this tile and then this moves to the left. So if the tile moves to the left, the picture that's underneath it has to move in the same direction in order for it to stay the same. So now it's working. Now we can see that we have these tiles and they are not just scanning across this texture, but they're taking the tiles with them. Okay, I think, yeah, the last one was maybe a bit advanced or a bit convoluted, but it's essentially just a synthesis of what we did here and what we did here. But instead of creating this outside of the jit.gl.pix, we just did it here in the for loop. But I think something's not right yet because I only can see 4 moving at the same time. So maybe... okay. Here you can see I just used numrect, so it would just take 4 of those, but we need essentially this here. So maybe we can use another variable, call this total rect or something like that. Then we can copy this thing here, put this in here, and then instead of using numrects, which will just use like the first part of this vector, we can use all 12 of them, and now we have the full picture moving around. Okay, so yeah. I hope this wasn't too complicated. So for me, these topics are all kind of related because it's always about, okay, instead of just using sampling as we did in the first part of the series in order to change or in order to transform one texture, we can also use sampling in order to access different textures and then, yeah, using this as a data container for position, for offset, or yeah, even for color as we did in the first one. So yeah, I hope you found this useful and thank you for watching.